for the. Oh, you got your own? Okay.
Cliff already knows that I'm going to go over, so he said, can you go 20 minutes? Anyways, good afternoon, everyone. I'll not try to do 20 minutes. I'll try my best to be quick. He mentioned about setting up of chiplet economy, and my talk is related to why chiplets are important, because that's an extremely important question to kind of talk about. And many of you are actually very familiar with the economics of chiplet in terms of the die size and the rationale. My talk is going to approach it in a very different way in terms of the use case, because this is something which is not talked a lot. I have not seen too many people talk about the use cases, so I um, presented a version of this talk at the Chiplet Summit in January, and that's what I'm doing basically here. So the arc of my talk is going to be very simple. We need to understand everything from the human use cases. What drives some of these technologies, and you want to connect them to the simplest of the rationale, not very complicated rationale, but something simple which always remains steady. Then next, I'm going to talk about how AI and ML has solved for these universal chiplets. What are the challenges which are coming because of AI and ML technologies advancing so fast? In fact, some of my slides talk about things which are in some sense already bit obsolete in 6 months. I created this presentation in December of last year, and generative AI has just taken over, so things are moving pretty fast. And then I'm going to talk about how chiplets solve these problems in the best possible manner, and hence, that's the right path to go forward. So let's start with the universal use cases. And these are the use cases which have been in existence for time immemorial. Since humans were walking in savannas in 100,000 years ago, I consider these as universal use cases. Recognition, mining, and synthesis. These drive everything what we have been doing for thousands of years. We are always interested in recognizing people. We are always interested in mining information, looking at the landscape, figuring out which berries are good, bad, and then synthesizing. We want to imagine things. Hey, bird is flying, so I can fly too. That's a synthesis. That activity has not changed, the context has changed, but the activity has not changed. Now let me give you context in the modern terms. And these are the things which I'm going to talk from perspective of some of the examples from Meta. And these examples themselves are changing so fast that you can see these examples emerge again and again. So recognition, in this particular case, Meta has built an engine which translates directly from 100 languages to another set of 100 languages without going through English. And this is very useful because this is how human beings can connect with other human beings faster. I'm in Prague here, I don't speak Czech, and imagine if I can communicate locally very clearly, that's helpful, and it's the case for everyone. So that requires certain amount of recognition which happens. There's an example of mining. Facebook, Meta has a lot of content online, and so do other companies. And you need to find ways to mine for harmful content so that you can keep your community safe. That also is a workload which you have to address. And then synthesis, I can't talk enough about synthesis. All of you actually are very familiar. I chose this example as a text to image many months back, thinking it was a pretty cool example. And guess what? Today, people are doing text to video. And that's synthesis, right? And I use Midjourney. I don't know if any of you have used a program called Midjourney. You can create some amazing images just by writing some prompts. So that's an example of synthesis. The interesting thing about all of these, they exist always. What has changed now is that AI/ML has been now the most effective method to address these use cases. I remember reading a paper in 2000 published by Intel where they talked about recognition mining synthesis, and they talked about different approaches. Problem statement was the same, approach was completely different. Today, the approach is very different, and something changed that approach. And that is something which I consider as a singularity event in terms of deep learning, and that was an event in 2012 which transformed the world towards this path, and that was discovery of LXNet. Many of you know LXNet. That was the first neural network which participated in a standing image competition, which was going on for many, many years. And LXNet became the first winner, which beat the second runner-up by over 10% margin. And within 2 years, Microsoft came up with a better version which actually could beat a human image recognition. And that led to massive explosion in using deep learning as a way to address workloads. I give an analogy of Cambrian Explosion. You saw a slide from Cliff's presentation. I created the version of that in 2019 based on inspiration from biology. When evolution happened 500 million years ago, there was an event in the history of biology called Cambrian Explosion, which led from very simple cellular and simple forms to myriad of complex forms within a short period of 10 million years. That's like, in evolutionary terms, that's absolutely like a Big Bang event. We are in that exact same moment in computation. For all the 40 years, the computation workloads were developing, but they were fairly normal, common, probably approaching from the scale perspective. With deep learning, suddenly the level of workload just exploded. People found this technology so effective that with tweaks and modification, they could start addressing things. And that is where we are today. And that has led to a whole bunch of new workloads which are becoming dominant. And I'll go through all of them. Ranking and recommendation, no surprises. You want to understand where people are, what interests are. Computer vision, again, no surprise. Language. And then multimodal models is what is happening today, where you feed in text, you feed in image, you feed in video, you feed in speech, and you can create some synthesis out of it. And all of these workloads are growing with their own needs, because we all love these kind of tools which we can use to create our own vision of things. And they actually can be scaled on 2 dimensions, memory intensity and arithmetic intensity. And when you look at it on 2 dimensions, you find that these workloads are not what a balanced application would be, which would scale linearly along with memory and compute. In fact, in case of CNNs, convolution neural networks, you find that actually they are very compute intensive and not as much memory intensive. But if you look at recurrent neural networks, or you look at recommendation systems, you find that they are very sparse. They require relatively less amount of compute, but massive amount of memory. And this actually is holding true even for generative AI, where you have to hold massive amount of memory. And the third dimension, which now we can start including in here, is the dimension of having network connectivity across various compute nodes. And that also is important, because the level of information you want to exchange is different among all of these workloads. And multimodal, I don't even know where exactly multimodal would fit, but I'll work on this and have an update version of this slide and publish it somewhere. So that's where the world is today. We went through deep learning, there are a new set of workloads emerging, they're solving very interesting problems, and they have been implications on system design. So what do we mean by system design? So all of this works on basic domain-specific architecture. GPU is an example of a domain-specific architecture, but a general term which we can use is something which is serving a specific workload. And typically for scaling, you're building a whole bunch of them together and putting it in a system. For example, Meta announced Grand Teton last Global Summit, which was made of 8 GPUs together. That's an example of a one Unix system, right? Zion system, which we released a couple of years back, Again, another example of that. And then you put all of these systems together to put a cluster. And this cluster is connected on the front end, and it's connected on the back end. On the front end, you have ways to kind of poll the cluster, calibrate the cluster, diagnostics, and on the back end, you are actually running all of the real network connectivity across these domain-specific architecture nodes, which you see here. NVLink is an example from NVIDIA, which is basically used for connecting at one scale and then InfiniBand at another scale. Yesterday, you heard from Ram Velaga, who is from Broadcom, talking about how Ethernet is now also working effectively to address back-end network. And Ethernet is traditionally used for the front-end network. So you kind of start getting appreciation of, okay, how the world is changing, how these things are changing, and what is happening. And all of this actually has a specific implication when you start looking at how these workloads demand various things, right? So on the left-hand side, you see how the number of parameters are there with regards to three classes here. You have yellow, you have blue, and you have green. So the yellow is GPT-based, which is basically generative pre-trained transformer model. Blue is the DLRM, which is basically recommendation model. And then green is your classic vision model, right? So you find that number of parameters required for DLRM and generative AI are huge, right? In case of Meta, we have been able to optimize things to the level where we actually, in spite of having massive number of parameters in our models, relatively speaking, we have less amount of flops, relatively speaking, required. And that's where you want to do some software optimization. However, all of this actually leads to some interesting challenge which domain-specific architecture has to address. I showed you a top-level view of how everything was connected. If you zoom in, you'll find that each of the nodes are connected across with other nodes in terms of you have a AI compute fabric, which is basically connecting through I/O network to your neighbors, and it's also connected to a memory pool because you need to hold these big models together. And there are three areas where we see you can have bottleneck. First, you want to increase the number of compute per node. So you want to increase your number of cores. Second, you want to have a faster access to the memory pool because that's where your model is sitting, parameters are sitting. You have to get those embeddings into your compute engine. You have to recalculate, put it back. And then you have to connect across many different nodes because you are running training cluster across large number of nodes. So all of these three areas actually lead to certain challenges. What are the challenges I'm talking about? These are actually classic numbers which have been published a while back. The key takeaway which you have here is that the rate at which the compute is growing versus the memory is growing is a different slope. You don't need to worry about the numbers, but the slopes are different. What it means is that you are going to, over a period of time, have compute which is moving faster and faster compared to the memory which can deliver what it needs to compute on. So half the time compute is just sitting around twiddling thumb, waiting for the data to arrive. And that's going to lead to loss of cycles, power, and inefficiency. And this challenge is actually growing because you're actually moving further and further towards the right-hand side. That is the place where domain-specific architecture can address. So the three challenges which I want to kind of summarize is you have accelerator memory gap, you have to have model flexibility because your workloads are changing very rapidly. I talked about 4 classes of workloads, DLRM, computer vision, RNN, and multimodal. And these are changing very rapidly. Today you have generative AI, which is a completely new type of workload. And then 2 years from now, 1 year from now, you'll have a completely different type of workload. You don't even know about it because somebody would come up with a new model to address it. And while you're doing your ASIC design, which takes 18 months, 24 months, your design is already obsolete by the time it arrives and becomes validated because now, okay, I have a new model, it doesn't work. And then the third is, I did talk about the bandwidth inefficiency because remember the backend network, which has to connect to all the nodes, it has to keep moving faster and faster. And that's the cross-sectional bandwidth, which also has to serve these training clusters. So these are the 3 challenges which we have as a result of the progression of AI, machine learning, and addressing the three classic recognition, mining, and synthesis needs, which we have forever. So how does chiplet help here? And this is where chiplets shine. So let me give you a couple of examples of chiplets can be used for addressing specific things. So you have, a domain-specific performance for accelerator memory gap. You're designing your system with your custom domain-specific accelerator with an on-chip network, and you have some amount of compute, FPGA, etc. And suddenly your workloads are going to change. You can go and actually build extra memory into the device at a relatively shorter development cycle. You still have a development cycle, but imagine if you're trying to do this in a monolithic ASIC, now you're stuck. You can't change amount of memory in a monolithic ASIC. You have to throw it away, and you have to tell, okay, we have to increase the memory by 4x. By the way, this is something which has happened multiple times in history of many of the companies. So this is a classic present problem. And now memory vendors can go and develop 3D stacking. They can develop different technologies. And in open standards, actually, there are companies which are working to develop open standards of working with memory and the DSA themselves. So that's addressing challenge number one. You also want to have a way to connect faster across your domain-specific nodes. Now you can do that using embedding of optical chiplets, as an example. Cliff mentioned about optical chiplets. That would be one other example where you could do this. Next, I want to talk about challenge number two. Challenge number two, you want to quickly go and change your system to have a different architecture for different use cases. In this particular case, you can remove domain-specific architecture for addressing AI/ML, and you can replace it with video transcoder, as an example. And that is an example where a lot of companies are working on creating video which can be served over iPhone and Android phone, on a big screen, on an iPad. You need massive amount of transcoding going on to basically allow for delivery of this content. You can do that very quickly. So that's challenge number two. Challenge number three, I talked about the networking bidirectional cross-sectional bandwidth. This can be addressed very easily by embedding optical switching chiplets across all of the networking switch. And in fact, there was a recent paper, I don't know if anybody saw the paper from Google on TPU4, where they are embedding something called OCS, which is based on MEMS technology. Now here you can have some kind of an interface between switch and optical chiplet, and then you don't need to worry about exactly what technology is used on the side of optical conversion, right? So you can have electrical to optical conversion, then optical conversion can carry on its own. So that's challenge number three. Now you can also basically do this with host interface direct memory access for addressing local host in a faster way for creating smart NICs. This is another example of using somewhat same architecture of your system in package, and you just change different chiplets from vendors, and you can build system at a shorter time cycle, maybe 6 months, maybe 8 months. Lot of firmware, lot of software, lot of security can be reused. You don't have to redo that for the ASIC. So that is the utopian vision of why chiplets could be very interesting in the coming decade, once you have a whole bunch of companies working together. There are challenges. There are a lot of things which we have to address properly. Economy has to be developed. I'm not saying that chiplet is the holy grail, apologies to Monty Python, but this is something we can try to aspire for, because if we are able to achieve, then on the other side, there is definitely a massive amount of gain for all the people in the economy to work together. Thank you.